Okay, so we're going to take a look at the first final exam practice. You're going to notice that one of the things that you're going to need to be able to do for drawing carbohydrates in general and sugars is to think about the 4 different ways that we can represent these carbohydrates. So there's the Fisher projection, which is an open linear chain, and then there are 3 methods of representing sugars. There's the Mills projection, which uses wedges and dashes to represent up and down. There's the chair form that shows up and down as well as axial and equatorial. And then there's the Hayworth projection that simply shows up and down, but without using wedges and dashes, only using straight lines. So I think one of the most important things that you can do is number your carbons. That's critical if you're going to be able to successfully complete this exercise. So notice your 1 is your anomeric carbon. Then if you take a look at your Fisher projection, you'll notice that the 5 is the penultimate carbon. This is the oxygen that forms the ether in the ring. When it comes to drawing mechanisms for the formation of a hemiacetal, my recommendation is simplify your life, make life a little bit easier. Go ahead and wrap the Fisher projection around, and then you actually are going to show the action of the nucleophile attacking the electrophile. Remember, you need to use resonance structures for your sugar in order to be able to represent this. And again, if you attack from the bottom, you're going to force the oxygen up. That's a beta anomer. If you attack from the top, you're going to force your hydroxyl group down. That's the alpha anomer. So when we're drawing the resonance structure for the aldehyde, the oxygen has a negative charge and the carbon has a positive formal charge. The hydroxyl on the penultimate carbon is the nucleophile, and the carbon with the positive charge is an electrophile. So this is an intra, not an intermolecular nucleophilic substitution, so it's an attack from within the molecule on itself, and it's going to form a ring. And again, if you're attacking from the top, that's going to be alpha. If you're attacking from the bottom, that's going to form beta. Now remember, right, alpha is the hydroxyl group down. Beta is the hydroxyl group up, which is kind of counterintuitive, so it's worth it to keep that in mind. Would beta-D glucopyranos have a low boiling point or a high boiling point? Why? So it's going to have a high boiling point because the glucose has 5 hydrogen bond donors and 6 hydrogen bond acceptors. That's a total of 11 possible hydrogen bonds. Number 2, the formation and reaction of proteins is critical in biochemistry. So remember the structure of the tripeptide KTN. So this is the predominant form that you're drawing at pH 7. You're going to assume that it's all trans peptide bonds. You're going to give the correct stereochemistry for your carbons in your linear chain. And then we're also going to label both the N and the C terminus. So if you recall when we've talked about doing this before, usually the best thing to do is actually to draw out our chain in its template form and then add our groups. Remember, you want to make sure that your wedges and your dashes are in the correct position. So wedge up, dash down. That gives the correct stereochemistry. Then the next thing we're going to do is actually look at the charge on the peptide. So our lowest pH is where everything is protonated. At pH 3, that's where our C-terminus carboxyl group is deprotected because of the pKa of 2.02. We have really no change. The next pKa is 8.95. So if we take a look here, right, we go from a +1 at the 7, where if we think about that, right, let's think about this. No charge, so this should be, let's check. So if it's -0, positive, that should be +1, right? That's at pH 3. At pH 7, are we deprotonating anything else? No, so it's going to stay the same. Right? Here, right, the next pKa is where we see a change. That's a pKa of 8.95. So once we get to 10, we're going to see this proton come off. The last pKa that we see is the 10.53. And that one then gives us an overall charge of -1. So if you want to think about it, there are 3 hydrogens that can be deprotonated. Don't get confused. The amide as well as the threonine cannot be deprotonated. We're not going to see those form ions. Then, without doing any more calculations, specify a range for the possible PI of the peptide and give your reasoning. So it's going to be somewhere between 7 and 14, likely around 10. Isoelectric point, again, is the pH at which the amino acid does not migrate in an electric field. This is the pH at which there is no net electrical charge or formal charge. Glycolysis is one of the central metabolic pathways. Remember, the metabolic pathway of glycolysis is shown below. Complete the missing steps. Your job here is to be Sherlock Holmes and to really think about what are the clues that are present. So here, the presence of hexokinase and magnesium tells me that I'm transferring a phosphate. It also helps that that phosphate has been highlighted. I'm going to transfer that phosphate onto the sugar, and in the process, I'm going to form ADP. Here, the ene diol is a double bond, remember? So I'm going from the aldehyde to the double bond to the ketone. That's a tautomerization, going from the keto to the enol form, and then shifting, right, from the aldehyde to the ketone. And then here, my job is to recognize that I'm adding an additional phosphate, taking that from ATP, so that means the enzyme I'm using has to be a kinase. I want to make sure that I use the counter ion magnesium 2+. So technically, the answer is phosphofructokinase. I'll accept either. In this case, all I really need you to recognize is that it's kinase. We think about a reasonable, complete mechanism for step 1 as shown. Again, this is the oxygen attacking the phosphorus. That's going to then form this intermediate structure, which then collapses, kicking out ADP and forming the phosphate. So the hydroxyl on the 6th carbon is the nucleophile. The phosphate is an excellent leaving group. The nucleophile attacks the phosphorus, the electrophile, the electrons then reform the double bond to the oxygen, kicking out ADP. The transfer of a phosphate requires a kinase and magnesium, which is not actually shown in the mechanism above because it actually binds somewhere else in the protein. How does pH affect the behavior of phosphates? Provide at least 3 examples of the molecular structure and behavior of ATP. So in glycolysis, it's step 1, step 3, step 7, and step 10. And if we think about the pKa's, so our first pK is 2.12, so we'll deprotonate 1 hydroxyl. Second pK is 7.2, and the third pK is 12.4. Nucleophiles and electrophiles are hidden throughout biology, as are oxidations and reductions. So, why are amines considered bases? What is the difference between an aliphatic and an aromatic base? So, if we think about this, a compound that can donate an electron pair to an acceptor, that's a Lewis base. Aliphatic bases have an isolated lone pair. That means they're going to be stronger. Aromatic have a lone pair in resonance, so they're going to be a weaker base. Formation of a Schiff base typically occurs between an amine such as ethylamine and a carbonyl group, such as 2-pentanone. Draw the mechanism below. Remember, here we have to draw a resonance structure for the carbonyl group. Our nitrogen then is our nucleophile. We're going to transfer a proton to the oxygen to form water, a leaving group. And then the lone pair on the nitrogen is going to form the imine, which is going to kick out water. Or I can actually also have, depending upon the available amount of the amine, another nucleophilic attack. But in this case, we're going to focus on our formation. Are we done yet? No, you could always do an additional transfer. And obviously, our amines could continue to react. So the electrophilic carbon of the ketone is attacked by the amine nucleophile, can form multiple products through additional amines such as nucleophiles or water, which can leave and then an imine is formed. So the imine, which we see up here, right, can only be formed really if we drive the reaction through the loss of water. This is the application. So Schiff bases are common enzymatic intermediates where an amine, such as the terminal group of lysine residue, reversibly reacts with an aldehyde or ketone of a cofactor or substrate. So the cofactor PLP is covalently bonded to the amino group of an active lysine, forming the internal imine. So PLP is drawn below. We're going to show this reacting with lysine. So this is my aldehyde. I'm going to make sure I draw the resonance form. This is going to react with lysine. My amine then is going to attack my electrophilic carbon. And that's going to result in the formation of an imine, also known as a Schiff base. Functional groups are critical to reaction mechanisms of biochemistry. So here are all of the functional groups that you need to draw and label. Notice I've also provided a key for how to organize them into the following categories. And then how many functional groups have lone pairs. You can arrange them according to the number of lone pairs. The question number 6, the relationship between structure and function is significant. So assign R and S to the following common medications for allergies and bronchodilation, ephedrine and pseudoephedrine. So here you're going to want to make sure that you assign both of the chiral carbons. And note, you can actually identify the relationships. These will be enantiomers. Right? These, of course, will be diastereomers. Draw the mechanism for the decarboxylation of malonic acid. You can redraw the molecule if necessary. Again, this is more mental gymnastics than anything else. Remember that this process forms the enol, which then can be reverted, in this case, to the carboxylic acid, as well as CO2. So the loss of carbon dioxide is decarboxylation. You're going to rotate the malonic acid into a pseudo six-membered ring conformation. This is a cyclic transition state. This results in an enol that tautomerizes to the carbonyl compound. You're going to start with protonating the carbonyl. You're going to break the hydroxide bond and form the pi bond. You're going to break the carbon-carbon bond and make the carbon-carbon. This is all concerted, though. It happens all at once. How is the mechanism for the formation of ADP from AMP different from the formation of NADH from NAD+? So one is an oxidation reduction mechanism. The formation of AMP to ADP is a nucleophilic substitution where phosphate is the leaving group. We're beginning to explore primary metabolites such as carbohydrates. In this case, we're going to focus on nucleotides and nucleic acids. We're going to label the nucleotides and draw the hydrogen bonds. We're also going to draw ADP and label the anomeric carbon, put a box around the 5' and the 3'. So here, this is the 5', so this is where my box would go. This is the 3', this is where my other box would go. And again, labeling the bases and identifying which are purines and pyrimidines. And then compare and contrast the structure and function of DNA and RNA. Provide at least 3 similarities and 3 differences. So structure, DNA is double-stranded, whereas mRNA is single-stranded. The function, we actually see genetic instructions versus messenger RNA, transport amino acids and to make proteins. There are some other structural differences, the deoxyribose versus the ribose, and the thymine versus the uracil. All right, thanks so much, folks. Hope you have a great day, and catch you next time.